Welcome back to the Deep Dive. We're continuing our series on computer science and software engineering
Oh, cool.
with a look at something pretty fascinating.
Okay.
NASA's 10 rules for safety-critical code development.
Yeah, it's a fascinating area where the stakes are incredibly high.
Right?
We're talking about code that controls spacecraft,
Wow.
airplanes, nuclear power plants,
Okay,
systems where even the smallest error could have catastrophic consequences.
so how does NASA make sure that this code is, rock solid, reliable?
Right.
They've got this legendary set of 10 rules
Yeah.
that act as this foundation for building software in these high-stakes situations.
And what's fascinating here is that these rules, while geared towards, life or death scenarios,
Right.
actually reflect broader principles of good software engineering that can benefit any developer.
The source material even calls them draconian.
Yeah,
But that makes sense given the potential consequences of a bug.
exactly. When lives are on the line, you can't afford to be lax.
Right.
Even the slightest possibility of error needs to be eliminated.
Wow.
The first rule really takes the tone. Keep the code structure super simple.
Right.
No goto statements, no jumping around.
Right.
And here's the kicker, no recursion.
Now, I've always found recursion to be an elegant solution in many cases.
Yeah.
Why is it such a no-go in this world of safety-critical code?
Well, recursion can create complex call stacks
Yeah.
that are difficult to analyze for potential errors.
Okay.
And remember, in safety-critical systems, verifiability is key.
Gotcha.
We need to be able to trace every possible execution path
Right.
and ensure it leads to a safe outcome.
Right.
And recursion, with its nested function calls,
Uh-huh.
can make that verification process incredibly difficult,
Wow.
introducing a lot of cognitive load for anyone trying to understand the code.
Oh, okay, so it's about choosing the most straightforward path,
Yes.
even if it might mean sacrificing, a bit of elegance in the code.
Precisely. And this leads us to the second rule,
Okay.
which focuses on keeping loops under control. Every loop needs a fixed upper limit.
Okay.
No endless loops allowed.
Okay.
You can imagine the potential problems with an infinite loop in a spacecraft guidance system.
That's a terrifying thought.
Yes.
A runaway loop on a Mars rover millions of miles away.
Right.
Talk about a debugging nightmare.
Exactly. A fixed upper limit ensures that the loop will always terminate,
Gotcha.
preventing the software from getting stuck and potentially causing a catastrophic failure.
Oh,
It's a simple rule, but incredibly important for ensuring predictable behavior.
okay. Rule number 3. Might raise some eyebrows.
Yeah,
No dynamic memory allocation after initialization.
right.
No mallocs or its friends.
Yeah,
For many programmers, this is a pretty fundamental tool.
sure.
Can you break down the reasoning behind this restriction?
Dynamic memory allocation introduces a level of uncertainty that's unacceptable in safety-critical systems.
Okay.
The size of available memory can fluctuate.
Right.
Allocation requests can fail.
Right.
And these uncertainties can lead to unpredictable behavior, even crashes.
Oh, wow.
Imagine a critical system running out of memory mid-flight.
Oh.
That's not a scenario we want to encounter.
Yeah, that's not good. So it's all about eliminating those unknowns
Exactly.
and sticking with a fixed, predetermined amount of memory from the get-go.
Exactly. A fixed chunk of pre-allocated memory ensures predictable behavior
Gotcha.
and eliminates the risks associated with dynamic allocation.
Okay.
It might seem limiting, but it's a trade-off for increased safety and reliability.
Now, this next rule is one I can really get behind, the one-page rule.
Uh-huh.
No function can be longer than what fits on a single sheet of paper.
Ah, yes, the one-page rule. This one often sparks debate,
Right.
but it speaks to a fundamental principle of software design managing complexity.
Gotcha.
Imagine trying to debug a function that sprawls across multiple pages.
Right.
It's a nightmare. You're constantly flipping back and forth, losing track of variables and logic flow.
Uh-huh.
It's a recipe for errors.
You're speaking my language. I've been in those debugging trenches,
Yeah,
and it's not a pleasant experience.
right.
I can definitely see how limiting, function length would improve readability
Yes.
and make the code easier to reason about.
Exactly. And that's not all. By limiting function length,
Mhm.
developers are forced to break down complex tasks into smaller, more manageable modules.
Right.
This modularity not only aids in understanding and debugging,
Mm-hmm.
but also makes the code easier to test and verify, which is crucial in safety-critical systems.
So it's not just about readability. It's about promoting good design practices that lead to more robust and maintainable code.
Precisely. Now, let's move on to rule number 5,
Okay.
which deals with a powerful tool for catching Beg's early assertions.
Okay.
NASA mandates a minimum of 2 assertions per function.
Wow, that's a lot. I've used assertions in my own coding,
Yeah,
but I've never seen them used so extensively.
sure.
What makes them so crucial in this context?
Assertions act as internal checks within the code, verifying that certain conditions hold true at specific points during execution.
Okay,
Think of them as alarm bells that go off if something unexpected happens.
okay,
If an assertion fails, it means there's a bug in the code,
right,
and we need to investigate.
right.
This helps us catch errors early in the development cycle,
Gotcha.
long before they can cause problems in the real world.
So it's like having a safety net built into the code itself,
Exactly.
preventing errors from slipping through the cracks.
Assertions help us build a more robust system by forcing us to explicitly state our assumptions about how the code should behave.
Right.
It's a proactive approach to error detection that's
Oh, yeah.
absolutely essential in safety-critical software development.
This is really eye-opening. These first 5 rules have given us a lot to think about.
Right.
It seems like NASA's approach is all about eliminating ambiguity and uncertainty,
Yes.
ensuring that the code behaves exactly as intended
Right.
every single time.
That's a great way to put it. These rules might seem strict,
Uh-huh.
but they're designed to eliminate any room for error in systems where even the smallest mistake could have dire consequences.
And we're just getting started. We'll be back in part 2 to delve into the next set of rules.
Great, so stay tuned.
Sound good? Welcome back to the Deep Dive.
Yeah,
We're deep in the heart of NASA's 10 rules for safety-critical code development,
right.
exploring how these guidelines shape software that, quite literally, has lives depending on it.
Yeah, these rules offer a masterclass in defensive programming,
Right.
a mindset that's valuable even outside of mission-critical systems.
In the last part, we covered the importance of simplicity,
Yeah,
controlled loops,
right.
and saying no to dynamic memory shenanigans.
Yeah.
Where do we go from here?
Rule number 6 brings us to the concept of data hiding.
Okay.
You want to keep data objects on a tight leash, limiting their scope to prevent accidental modification from other parts of the code.
So it's like creating a secure compartment for sensitive data,
Right.
minimizing the blast radius if something goes wrong elsewhere.
That's a great analogy.
Okay.
Think of it this way. If a piece of data is only accessible within a specific function,
Okay.
it's much less likely to be corrupted by errors or side effects from other parts of the program.
Right.
This promotes modularity and reduces the risk of unintended consequences,
Gotcha.
both crucial in safety-critical software development.
This makes me think about some of my own coding projects.
Yeah.
I've definitely learned the hard way about the dangers of global variables and unintended data modification.
We've all been there.
Yeah.
And this principle of data hiding goes hand in hand with rule number 7,
Okay.
which focuses on the often overlooked return values from functions.
Right. It's easy to just assume everything went smoothly.
Yeah.
And ignore those return values, especially for like seemingly simple functions like printf.
Yeah, in safety-critical systems, that kind of assumption can be dangerous.
Right.
Ignoring return values is like driving with your eyes closed,
Oh, wow.
hoping for the best but not really knowing what's going on under the hood.
Yeah.
Return values provide crucial feedback.
Uh-huh.
They tell you whether an operation succeeded or failed.
So if we connect this to the bigger picture,
Yes,
it's about maintaining a constant awareness of the state of the system,
right?
never making assumptions,
Yeah,
always verifying.
precisely. And this vigilance extends to rule number 8,
Okay.
which might surprise some people,
Okay.
taming the preprocessor.
Oh, right.
Now, the preprocessor is a powerful tool,
Yeah.
but it can also make code harder to read,
Huh.
understand, and analyze.
Yeah, it's like adding too many layers of abstraction.
Right.
You might end up with code that's, elegant but difficult to decipher,
Yeah,
especially when you're trying to track down a bug.
exactly. And that's why NASA limits preprocessor use.
Okay.
They want clarity and transparency in the code.
Right.
If you relied heavily on macros and conditional compilation,
Yeah.
it can become incredibly difficult to trace the actual logic flow and verify that everything is working as intended.
So it's about striking a balance between the power of the preprocessor
Yes.
and the need for clear, analyzable code.
Absolutely. And this brings us to a perennial source of both fascination and fear among programmers, pointers.
Oh, yeah.
Rule number 9 lays down the law: only one level of defensing allowed and no function pointers.
Now, pointers are a fundamental word of C and C++.
Yeah,
The language is often used in these safety-critical systems.
right.
Why such a strict limitation on their use?
Pointers give you direct access to memory,
Right.
which can be incredibly powerful, but also incredibly dangerous if not handled with extreme care.
Okay.
They can lead to memory leaks,
Yeah.
dangling pointers,
Right.
buffer overflows,
Right.
all sorts of nasty bugs that are notoriously difficult to track down and fix.
Right.
And in a safety-critical system, those kinds of bugs could have disastrous consequences.
So by limiting pointer usage,
Yes.
NASA is essentially reducing the potential attack surface for these types of errors,
Exactly.
making the code more predictable and less prone to, like, those hard-to-find memory-related bugs.
Exactly. It's about minimizing risks.
Okay,
Yes, you might sacrifice some flexibility,
right,
but the trade-off is increased safety and reliability.
right.
Remember, we're talking about systems where even a small memory leak could eventually lead to a complete system failure.
Oh, wow.
So,
It's like choosing to walk a well-marked path rather than venturing into a dense, unexplored forest
yeah,
where you might encounter unexpected dangers.
I like that analogy. It highlights the importance of choosing the safest route,
Right.
even if it might seem less exciting or efficient at first glance.
And finally, we arrive at rule number 10,
Yes.
which emphasizes the importance of maintaining a, like, ruthlessly high bar for code quality
Right.
through rigorous testing and analysis.
Exactly.
This is where the zero warnings mantra comes in, right?
Yes.
No warnings during compilation
Right.
and daily checks with static code analyzers.
Exactly. This rule underscores the relentless pursuit of perfection that characterizes safety-critical software development.
Wow.
Every potential issue, no matter how small,
Yeah.
must be identified and addressed.
Okay.
And static code analyzers play a crucial role in this process.
So it's like having an army of automated code inspectors constantly scrutinizing your work,
Yeah.
ensuring that it meets the higher standards.
Right?
They can catch potential problems that might escape even the most diligent human reviewer.
Exactly. Static code analyzers are incredibly valuable tools for detecting a wide range of issues, from style violations to potential security vulnerabilities,
Right.
and even subtle logic errors that might otherwise slip through the cracks.
Wow.
This continuous automated code review is crucial for maintaining the integrity of the system over time.
This final rule really highlights the level of discipline and rigor
Yes.
required in safety-critical software development.
Exactly.
It's not just about writing code that works.
Right.
It's about writing code that is verifiably correct, reliable,
Yes.
and robust enough to handle any situation.
Absolutely. And while these 10 rules were initially developed for mission-critical systems, the principles they embody,
Right.
clarity, simplicity, predictability,
Okay.
and a relentless focus on quality,
Right.
are relevant to any software project where reliability and robustness are valued.
I think that's a key takeaway for our listeners.
Yeah,
Whether you're building a web app,
right.
a mobile game,
Uh-huh.
or even a simple script,
Sure.
these rules offer valuable lessons on how to write better, more reliable code.
Yeah, these rules offer a window into a world where software isn't just about functionality.
Right.
It's about trust and ensuring that the systems we build behave as expected,
Right.
even in the most demanding circumstances.
And that brings us to the end of part 2.
Okay.
We've covered a lot of ground, but there's still more to explore.
Right.
Join us in part 3, where we'll wrap up our deep dive into NASA's 10 rules for safety-critical code development.
Sounds good.
Welcome back to the deep dive. We've been on quite a journey exploring this meticulous world of NASA's 10 rules for safety-critical code development.
Yeah, these rules offer a glimpse into a world
Right.
where software failures aren't just bugs, they're potential disasters.
We've talked about simplicity, verifiability, data hiding, taming pointers. It's like a masterclass in building software that absolutely
Right.
positively has to work.
And now we arrive at the 10th and final rule,
Okay.
which really ties everything together.
Okay.
It's all about maintaining a ruthlessly high bar for code quality.
Right.
No compromises allowed.
We touched on this earlier, the zero warnings philosophy,
Exactly.
no warnings during compilation,
Right.
and daily checks with static code analyzers. It sounds intense.
This rule speaks to the seriousness of safety-critical systems. Even a seemingly minor warning
Right.
could be a symptom of a deeper problem,
Okay.
something that might not manifest immediately but could have serious consequences down the line.
So it's not just about making the compiler happy.
No.
It's about understanding that even a small warning could be a canary in a coal mine.
Precisely. And static code analyzers are those canaries.
Right.
They go beyond simple compiler warnings, looking for potential issues like style violations, security vulnerabilities,
Yeah.
and even subtle logic errors that might escape human review.
It's like having a team of expert code reviewers
Right.
constantly scrutinizing your work, making sure every line meets the highest standards.
That's a great way to think about it, and it's not just about finding problems, it's also about preventing them.
Okay.
By using these tools regularly,
Right.
you're building a culture of quality,
Okay.
encouraging developers to write cleaner, more robust code from the start.
So it's a continuous process, a commitment to excellence that extends throughout the entire development lifecycle.
Absolutely. And this commitment to quality is really at the heart of all 10 of these rules.
Okay.
They represent a philosophy, a way of thinking about software development that prioritizes safety,
Uh-huh.
reliability, and predictability above all else.
It's fascinating how these rules, which were developed for such specialized systems,
Yeah,
actually embody principles that any programmer can benefit from.
exactly. Whether you're building a mobile app,
Right.
a web service, or even a simple script.
Right.
These rules offer valuable lessons on how to write better, more reliable code. Think about it.
Right.
Who wouldn't want their code to be as robust and error-free as the software that controls a spacecraft?
It's a reminder that while technology and programming languages might evolve,
Right.
the fundamentals of good software engineering remain timeless.
And it's a testament to the incredible impact that software can have. When crafted with care and precision,
Yeah,
it can push the boundaries of human achievement, explore new frontiers, and even save lives.
well said. And on that note, I think we've reached the end of our deep dive into DAS's 10 rules for safety-critical code development.
It's been an insightful journey exploring a world where software engineering meets the highest stakes imaginable.
We've learned about the importance of simplicity, verifiability, and an unwavering commitment to quality.
And while most of us may never write code that controls a rocket launch,
Right.
the principles we've discussed today can help us all become better programmers,
Yeah.
building software that is more reliable, more robust, and ultimately more valuable.
So to our listeners, let this be a reminder that the pursuit of excellence in software development is a journey worth taking,
Right.
no matter the destination.
Thank you for joining us on the Deep Dives. Until next time, happy coding.